Objective 6 is going to come in two parts, A and B. So A is part 1. In another day, we'll do part 2. And it's going to be more optimization problems. They might be just a little bit different. I guess you could call them a little bit tougher. And optimization is just an application of maximums and minimums. All right, so these are a type of word problem. So we're going to start by writing that out. We have a manufacturer wants to design an open box, which means there's going to be no lid. It needs to have a square base, and a surface area of 108 square inches. Here's our question. What dimensions will produce a box with maximum volume? So the end question is find the maximum of the volume. Again, we're finding maximums and minimums. That's the application here. So the end question, the last thing you want to answer, is find the maximum of the volume. So if I want to find the maximum or a minimum of a function, if we had a closed interval, remember we tested endpoints and critical numbers. Here all we're going to have are some critical numbers. So we actually need to come up with a volume formula to find the critical numbers of that volume. Right. But we'll build and get to that step by step. So let's start with a sketch. So if you can draw a picture, draw a picture. This way you can label some things, and that will help us build our equations. So I have an open box that has no lid, and it needs to have a square base. Okay. So a square base, all the sides are the same down here on the bottom. And remember that there's no lid here, so this is open on top. That way, when we talk about the surface area of this box, we don't include the top surface since there isn't one. So let's go ahead and label our box. So the base, let's say it's measuring x by x. Since those two sides have to be the same because it's a square, we want to call them the same thing. Now the height is something different. We don't know, and we don't know how it relates to x. So let's just call it h. Okay. And then we're going to come up here with the surface area of this box. Okay. So a few things you want to do here. We start with our sketch. The next step is we want to come up with equations. Step 2. We labeled it so we can come up with our two equations. There are two equations that each of these optimization problems have. Okay. The first equation is going to be using our known values. That problem here would be the surface area. We know the surface area, and we can write an equation involving the surface area. So the total surface area here, 108, should be the sum of the area of all the surfaces. So our base measures x by x, so its area is x squared. The front side measures x by h, so does the back. And the right and left sides also measure x by h. So we have more x by h's. The base, we have 4 sides but no top. So altogether, I have x squared plus 4xh. All right. Our second equation is going to be what we want to maximize or minimize. And in this problem, you were told to maximize the volume of the box. So we're going to build the volume equation for the box. So we don't know what this volume is. We just want it to be a maximum value. But we can write it out in terms of our x's and h's. So the volume, length times width times height, x times h, will give us x squared h. So we now have our 2 equations. So the third step, to find that maximum of the volume, remember to find the maximum, we want to find its critical numbers. We need to take the derivative and set it equal to 0. So find the derivative of what you want to maximize or minimize, depending on the problem, and then set that equal to 0. So there's one more thing we have to do here, why we have 2 equations. Before I can take the derivative of the volume, I can't have 2 different variables in my volume equation. So we're going to use the known equation to make a substitution into our unknown equation. Okay? So I don't want x and h, I just want x or h. I'm going to take this equation here with the known values, and we're going to solve for h. That would be the easiest value to get by itself. So taking this equation to the side over here, and solving for h, dividing by 4x, so we have h is 108 minus x squared over 4x, and that is going to substitute right back into our volume equation. So the volume is x squared times 108 minus x squared all over 4x. We want to take the derivative of this equation, but if I simplify it first, we'll have a nicer function to differentiate or to take the derivative of. So I'm going to simplify this. So let's get our volume into a nice form. First, I can reduce one of the x's. That will leave me with x times 108 minus x squared over 4. And then I can distribute the x. So 108x minus x cubed all over 4. And really, I could just split these up into 2 parts, so I don't have to use my quotient rule. So 108x over 4 minus x cubed over 4. And so we'll use this to take our derivative. So up here, I'm going to write down the volume formula again. So 108 over 4 is going to reduce to 27x. And this is 1/4 x cubed, or x cubed over 4. And now we're ready to take the derivative and set it to 0. We get 27 minus 3/4 x squared. Set that equal to 0, and we solve for x. We're looking for critical numbers. So add the 3/4 over. Then we're going to go ahead and divide by 3/4 or multiply by 4/3. That's going to give us 36. So x would be plus or minus 6, but x is a length. So I want to make sure I just have 6. So the base of my box is a 6 by 6. Now I just need to find the height. So my question, what dimensions will produce a box with maximum volume? I've maximized the volume. I've found its critical numbers. And I need to give the dimensions. So I know it measures 6 by 6 by something. So if I go back to my equations here, I have an equation that involves x and h. And so I'm going to plug 6 back in here for x and solve for h. If I go down here, I already have what h equals in terms of x. So I can just plug 6 in here. 108 minus 36 over 24. And that will come out to 3. So the length and width are 6. The height is 3. So my final answer, my dimensions here, would be 6 inches by 6 inches by 3 inches. The last step you want to do on each of these problems is justify. So to justify that you have a maximum, you just want to show that your critical number is the maximum on a number line test. So here's our justification. So C prime, we would put 6 on here is a 0. And then I just need test values to show I have a maximum. So 1, 10, plug those into our derivative. If we plug in 1, we get a positive. If we plug in 10, we get a negative, and that right there verifies that 6 is a maximum value. So we've maximized the volume of the box. So in example 2, we are looking for points on the graph of y equals 4 minus x squared that are closest to the point 0, 2. So earlier we talked about drawing a picture first. So we can do that here. Y equals 4 minus x squared is a parabola. Okay, so step 1, let's draw our picture. We're looking for points on our parabola that are closest to the point 0, 2. So 0, 2 is going to be right here. Okay. So we have two equations that we're supposed to have. Remember the known and then the unknown one. So step 2, I have a known equation. This time I don't even have to write it. It's already written for us. Y equals 4 minus x squared. Okay, and then we also need our unknown equation. Well, that's going to be what we're trying to do here. We want to make points close as we can to the point 0, 2. So in this kind of problem, when you're looking for proximity, what we're trying to do here is minimize the distance between two sets of points. So our unknown or the one we're trying to minimize here is our distance. Our distance formula. So it's the distance between an unknown point, xy, and a known point, 0, 2. So this is our unknown equation and what it will look like. Okay, and again, saying that we want to find points that are closest to another point really means what we want to do is minimize the distance between them. And whatever function it is you're trying to minimize or maximize, remember to find the minimum or maximum. We're looking for critical numbers of that. So we want to take the derivative here and set it equal to 0. First thing though, we can't do that until it's all in terms of one variable. So we can't work with this just yet because it's in terms of both x and y. So we're going to take our y equals equation here and substitute it into here. So now my distance equation, 5x minus 0 squared is just x squared, plus y, which is 4 minus x squared, minus 2 squared. That will simplify. And there it is. Now I don't want to multiply out what's underneath, although you can. It's unnecessary, so we won't worry about that right now. What I do want to do next is my third step. I need to take the derivative of this function and set it equal to 0. Well, when I take the derivative of a square root, you should have noticed a bit of a pattern. We always get 1 over 2 times the original root, all this stuff here, times on top the derivative of what's inside. So that would be 2x plus, here we're going to use our chain rule. So power rule first, 2, drop the power rule 1. And the derivative of what's inside, negative 2x. Now if I set any fraction equal to 0, the way we solve for where a fraction is equal to 0 is only when the numerator equals 0. So I don't even need the denominator here. We're just going to take our numerator, 2x, and I can start working this out. So I've got negative 4x times 2, and then negative 4x times negative x squared, so positive 4x cubed. And again, we're setting that equal to 0. We set our derivative equal to 0, the fraction equals 0 only when the numerator equals 0. So I have 4x cubed minus 6x is equal to 0. This one's friendly enough. We can solve this by hand with just a little bit of factoring. If it weren't, we'd probably need our graphing calculator to get these values. So I have either x is 0 or x squared equals 3 halves. So x equals plus or minus the root of 3 halves. So I'm looking for the closest point, the minimum distance. So out of these values, these are all critical numbers. I need to know which of them will give me my minimum. You can look at the graph and it might help you. So when x is 0, we're at the point 0, 4. And I know this distance is 2 units. I don't actually have to find the distance to know which ones are closest. Plus and minus root 3 halves, okay? Somewhere in between here and here. Those are likely going to be my closer points. Okay, so what we're going to do is just do our justification now and figure out which values are our minimum values. So on the side here, we'll do our line test for justification. We'll put 0 on. There's a 0 of the derivative, plus and minus root 3 halves. Okay, and test some values in between. So picking some other numbers here. Go way out, and then we can choose some other numbers in between here. Just plug those back into our derivative. So plugging in a number like -5, we're going to end up with a negative. Plugging in -1/2 or -1, we'd end up with a positive. Plugging in 1/2 or 1, a negative. Plugging in a number greater over here would be 2, 3, 4, 5. We'll end up with a positive. So I can see a change from negative to positive minimum. And another negative to positive over here is a minimum. A change from positive to negative for our derivative would be a maximum. And you'll notice there's lots of points that are even further away from 0, 2 than the point 0, 4. So that's why you're not being asked for a maximum here. It's not possible to find one. And we don't want this value anyway. Okay. So these are going to give us our minimum values. And again, we're looking for which points on the graph of the parabola are closest to the point 0, 2. So I found the values that give me my minimum. Okay, the x values plus and minus root 3 halves. If I want the point, I just need their corresponding y values. So we do need to plug these numbers back into our function. So I guess our last step is positive. Their corresponding y values. So these go back into our equation here for x. So we'll end up with y is equal to 4 minus. If I square these numbers, we just get 3 halves out. 4 minus 3 halves is 5 halves. And then we already did our justification over here with our number lines. These are those coordinate pairs that we need. So this is a tough example. There's a lot of work that goes into it. We have to figure out what our two equations are that we need. One is given, the other one that's unknown. It's not very clear what it is we're trying to do. So watch out for this problem. It will come up several more times. It always is talking about minimizing the distance here between 2 points. So you do need to know your distance formula. Remember, another key thing is you always have to have one variable before you take your derivative. Let's add that in. So one variable before you take your derivative. And then with a square root function, just know that all you really care about in the end is the top of that fraction. And you'll notice the top of that fraction was just the derivative of what's inside. So that's really all that mattered here in this problem. And then again, if this came out to a function that wasn't very nice that we could do by hand, you might use your calculator to solve for these values to finish the problem.